maybe we should start already. It's my pleasure to welcome Vince Contizer to give this week's lecture. And I don't know if you can share your screen, if you've tried already to share the screen.
Yes, I'll share it now.
Okay. And Vince will talk about designing agents, preferences, beliefs, and identities. And during the talk, I guess there will be a bunch of quizzes. So I'm looking forward to your talk. Please take it away.
Thank you so much. So can you see the slide and hear me okay? Great. All right. Well, thank you very much for inviting me to give this talk. I'm Vince. My main appointment is at Duke University. I now also have an appointment at Oxford at their Ethics in AI Institute. As Rupak said, we're going to have some polls. The polls will all be completely anonymous, not for any credit. But don't hesitate to participate, please. And generally speaking, I'm happy to be interrupted with questions. It's a pretty broad talk, talking about a lot of different things. The most interesting thing, I think, in a workshop is to find something of common interest. So if I don't get through all my slides, that's totally fine. Better that we have an interesting conversation. So please do interrupt me. Rupak said he would monitor the chat for me. Thank you very much. And so, yeah, don't hold back. Great. So this is a talk about designing agents' preferences, beliefs, and identities. And to introduce it, I start with this little story here on the right-hand side of the slide, where I want you to imagine two self-driving cars, the two autonomous vehicles. And the orange one pulls up behind the green one and starts to kind of tailgate the green one and gets very close behind the green one and sends a message. And the message is, well, if I tailgate you, will your occupant take back control and pull over? Right. So this is still a self-driving car where a person can take over the wheel. And one thing to keep in mind here is that if you're a self-driving car, that is one of the worst things that can happen to you, right? Total loss of face, your occupant takes over. So you don't want that to happen. And so as a result, the green car rather nervously says, oh, what makes you think I would tell you? And the orange car says, hi, he's nervous, right? So you just told me, you better get out of the way now. You're bluffing. Oh, are you willing to take that chance? So the story is supposed to be a little bit funny. I don't know if it is, but if it is funny, the reason it's funny is that obviously this is a very anthropomorphic way of thinking about self-driving cars, right? And we kind of realize that that's presumably not really how self-driving cars would work. And that's maybe why it's a little bit funny. And yet I would argue that in AI, we're often taught to reason in kind of that way and to think about our AI systems in that way. Russell and Norvik, Stuart Russell is at Berkeley. Their textbook is probably the main textbook in AI used in academic AI courses. And now, at least in older versions of that textbook, you're presented with this model of an agent. So the idea is that what we want to build in AI is agents. And an agent is this really nice kind of well-delimited modular entity that first of all has sensors to observe the environment. From that builds a model of the world, has a model of the world, also has a model of, as it takes actions, how will the state of the world change? It also has some sense of utility or preferences or some objective function that measures how happy it would be with certain states of the world. And based on that, it can make decisions. It has effectors or actuators, something that makes a difference in the world to change the environment in a way that makes it happier, right? That's the idea. And on top of that, in the text, it says, well, so where does this utility function come from? Well, how do we decide how happy the agent is with various outcomes? And we say, well, that has to somehow come from outside. Somebody has to tell us what is the objective function. What is it that we want to be pursuing? And there's sort of a, no arguing about tastes thing there. Whatever the objective function is, that's what we're going to optimize, right? That's the typical picture that I think many of us have been introduced to when we first took our first AI course. And I should say, by the way, Stuart Russell now these days doesn't really believe in this picture, especially the part on the right anymore, right? And he is actually doing a lot of work. He and his students are doing a lot of wonderful work on thinking about how you really should be learning the objective function, how you should think about what that is. So this doesn't really reflect Stuart's current thinking anymore. And those of you who are at Berkeley, I encourage you to check out his group's work. But this is kind of the standard picture. And I would argue that this picture has come under a lot of pressure when you look at real AI applications as we see them today. So one example of that would be a network of self-driving cars. So imagine that you actually control all the self-driving cars in some town, right? Maybe there's not even any other human-driven vehicles. You control all the self-driving cars. So you control this whole network in some sense. And now the question is, should you think of this entire system as a single agent? Or should you maybe think of individual cars as agents? And it's not really clear, right? So you can ask yourself all these questions. Well, should the whole network pursue the same global objective? And then if so, what should that be? Or should maybe the individual vehicles have different objectives, different preferences, right? Maybe you would like your own car, the one that you sit in, to act in your best interest, right? And people have argued maybe that's a good idea because otherwise people won't adopt these vehicles, right? If the vehicle is likely to sacrifice you for the benefit of others, maybe people won't adopt those vehicles, and then we don't adopt this life-saving technology. But others have argued differently, right? So it's not clear in terms of the objective function or the preferences where the boundaries of one agent are. Where does one agent end and where does the other begin? And you can say the same thing about beliefs, right? So maybe the whole system should just have one big belief state of the entire system. But then again, maybe I don't want your self-driving car to know where I just came from, right? Maybe there are some privacy concerns, at which point our cars would have different knowledge and different beliefs. Okay, so that's one kind of example where we see that the boundaries of agents are maybe a little bit fuzzy, and also they might change depending on whether you're considering the objective or beliefs or something else. Another example not on the slide would be personal assistants, like the ones you have on your phone. Let's say Siri, Apple's personal assistant. In that case, too, this is actually something that the AI community has been thinking about for a very long time, right? This has always been kind of a dream of the AI community that we would have these personal assistants that are AI agents. But the way that that's materialized, I think, isn't quite the way that the AI community imagined it, right? Because the AI community imagined something more like what we saw on the previous slide. I have my assistant that really acts in my best interest and has its own model of the world and so on. Whereas that's probably not really true for Siri. Right? If on my iPhone I have Siri running, is that really my copy of Siri? Well, no, right? There's just this big entity in some sense of Siri all over the place. But then again, maybe it's not like sharing all my queries with all the other phones either, right? So it's a little bit ambiguous. So just to kind of push a little bit more on this anthropomorphic idea, right? So I think typically when we think about an agent, we have this idea of maybe like a human being that persists over time, right? Over the course of this person's life, that person makes a bunch of decisions and also learns a bunch of information that it can base those decisions on, right? And presumably remembers that information. I forget stuff all the time, but there's no kind of systematic forgetting, right? And so this idea of the agent really persisting over time is a reasonable model. But with AI, well, AI is software, and so you can run it multiple times. You can instantiate it multiple times, and you might have multiple instantiations of the same software in multiple places. And each one of those instantiations is going to make decisions. It's going to learn different things about the world, right? Some of them might communicate with each other. Here, somewhere in the middle, you see this green arrow turning into a black arrow, so that's intended to be a communication action, but not necessarily, right? Maybe not everything is shared, and so all these copies have potentially different beliefs and different objective functions that they pursue. So this really leads us into questions of philosophy, right? These kind of questions of what should we want? What is the good life? What are morally praiseworthy or wrong actions? That's, of course, what you might see in philosophy courses and in ethics courses. And then also questions such as, what makes one thing part of a larger object, right? What does it mean for an object to persist over time? What does it mean for a person to persist over time? They're very classical philosophical questions. And looking at these from the AI perspective, I think really gives a new perspective on them, and also a very concrete one that I think is helpful. So that's all that I wanted to say for the sake of introduction. And now I want to talk a little bit about, so what is the rest of the talk going to be about? So I'm going to split it into two parts. The first part is going to be focused on this issue of learning the objective function for a system, right? What should the AI pursue? And I'm going to focus there especially on moral reasoning. So settings where there's some ethical element to the decision making. And we're also going to get a little bit into social choice theory. Social choice theory is the theory of how do you make a decision when multiple people disagree about what that decision should be. That's going to be the first half of the talk. And then in the second half, I'm going to talk a little bit more about these questions that are related to this issue of where are the boundaries of agents. And I'm going to look at decision and game theory questions in those kind of contexts, which I argue are different from the ones that typical human beings would face. So that's the outline. Great. So first, let's talk about objective functions, in particular in moral decision making. So here our goal is to do automated moral decision making, where an AI system can itself make moral decisions. And we'll see some examples of why that would be useful in just a little bit. The two collaborators here on the left side of the slide are Walter Sinnott Armstrong, who is a professor of philosophy, is a professor of practical ethics at Duke. Here you see him in a straitjacket, but normally he's not in a straitjacket. And Jana here is now an assistant research professor, also at Duke, in our Social Science Research Institute. And the three of us, a number of years ago, put together a grant application and started working on this in earnest. And the first thing that came out of this was this paper where we had two different frameworks for automated moral decision making. The first one was based on game theory. And so I'll start briefly with that one. But actually, most of our time has been spent on a framework that's more based on machine learning. So in particular, looking at the kinds of decisions that human beings make in contexts where there are some ethical elements to the decision being made, and then trying to generalize from those, right? So the idea being that if you can predict what humans would have done or say they would have done, then you could also make that decision yourself as the AI system. So those are the two main approaches. Let me briefly touch on the game theory one, since after all, that's one of the topics here. We'll see more game theory in the talk later as well. Good. And also we'll have our first poll question here, so please be ready. So this game, I'll call the parking game. We have our two friends, the self-driving cars, and they're trying to park in some kind of parking lot. Okay. The orange car is trying to park, and it turns out the brown car here in the middle of the slide is about to pull out. You can see maybe a person is loading up the groceries, or it's not quite ready to get out yet, but it's going to leave pretty soon. Okay, and so the orange car stops and waits for the spot to clear. And meanwhile, a green car pulls up behind it, also a self-driving car, let's say. It doesn't really matter if they're self-driving or not, but let's say. Now, my drawing is not great, but this red block here on the left-hand side, that's a wall, okay? So right now, the green car is kind of stuck. And now it's kind of up to the orange car. The orange car could just sit there and wait, in which case the green car is stuck. Or the orange car could pull here to the left where you see those yellow lines. And those yellow lines mean you're not supposed to park there. But the orange car could briefly pull in there to let the green car pass, right? And maybe the green car even sends a message and say, hey, orange car, I know you're waiting for that spot of the brown vehicle over there. I understand, but would you please let me pass so I can keep looking for my spot? Okay, that's the setting. And of course, if the orange car passes, then the green car can go ahead and keep looking. But another thing that the green car could do is steal the spot. Okay, that's the thing that the green car could do, could steal the spot vacated by the brown car. And if you draw this as a game, here's what it might look like. Here's an extensive form game. Orange car can wait, in which case that's it, right? There's nothing, no other decisions to be made. Orange car is pretty happy, gets a spot. Green car is not so happy. So 3, 0. On the other hand, the orange car could move aside, in which case the green car could pass. Right? In which case, the green car keeps looking for a spot, and the green car is a little bit happier. So now has a utility of 1. And let's say also the orange car is a little bit happier with this outcome because there's no longer a green car sitting behind it being kind of annoyed. But alternatively, the green car could steal the spot, in which case the green car gets the spot and a utility of 3. And of course, the orange car is very unhappy now. Okay, now your straightforward game theoretic analysis might say, well, the green car, if given the opportunity, is going to steal the spot because that will give the green car a utility of 3. That's better than 1. And the orange car will anticipate that, and so hence will wait and not vacate, not get out of the way, right? So that's backward induction. That's the unique subgame perfect equilibrium, if you will. And it's a little bit frustrating because actually that outcome is worse for both players than if the car had moved aside and the green car passed. Of course, that's the kind of thing we often see in game theory, that due to selfish behavior, an outcome is reached that is worse for everybody than if everybody had coordinated. So there's, in that sense, there's maybe not much new there. But what I want you to think about is it morally wrong for the green car to steal the spot? Right? Imagine maybe also the orange car sends a message back and says, okay, I'll move aside for you so you can keep looking, but don't steal the spot, right? That's not the point here, right? I'm trusting you not to steal the spot. So first poll question is going to be a simple one. If I can find the poll, yes, I can. Again, all the polls will be anonymous. Here's the first poll. Is it morally wrong to steal the spot? Let's see if we get some answers. Okay, good. And I'll share the results in just a little bit. And again, I want to think about this so first of all, there's a question of what would people do? And there are a lot of experimental studies on a very related game called the trust game, in which is a little bit different, but basically experimentally people do move aside and they do then actually pass. They don't steal the spot, or that's or the analogous outcome would happen in the trust game. But I want you to think normatively, like what is the right thing to do? I'm going to end the polling. I'm going to share the results. So it turns out almost 80% of people who responded said, yes, it's wrong to steal the spot. And another 19% said, it's kind of wrong. And one person said that, no, it's not wrong. Okay. So those are our results. So you might worry that game theory is somehow missing something in its standard solution concepts, right? And so we've done some work on, and this is really where I kind of got started with ethics, was thinking about game theoretic solution concepts that capture some of these ethical constraints. So that's one of our lines of reasoning. And so I think that works nice for this kind of thing where there's an issue of betraying somebody's trust. But there are so many reasons to do things in ethics that I'm a little bit pessimistic about capturing all of those with game theory. And so we focused more on this other line of work where we think about looking at human judgments of what is the right thing to do, and then just trying to learn what humans tend to do. And if we can learn that well, if our AI system can learn that well, then actually the AI system could also take those actions itself. And you might have a couple of worries with that approach. So let's start right away with addressing those. First of all, whose preferences or whose values are we going to model, right? Generally, if you ask me some of these questions of what the right thing to do is, they might disagree with somebody else. And so should we go with my values or somebody else's? Probably we shouldn't just go with one individual's values, but we should somehow aggregate, right? Maybe we actually have people effectively vote over what the right thing to do is. And this brings us into social choice theory. I'll say a little bit more about that in just a second. Another concern you might have is that, well, this kind of leaves us stuck at human level moral decision making, right? If humans are morally terrible, then these systems will also be morally terrible. And that is very much true. That's a limitation of this approach, though I'm a little bit optimistic that in some ways it might be better, right? Because I might have my own moral failings and lack of insight in some cases. So maybe I make the wrong judgment some of the time. But as long as that is idiosyncratic and somebody else has different moral blind spots and somebody else has different moral blind spots, we might kind of vote out all of these errors. That's maybe a hope. But I don't want to dismiss this point. I think that is a concern. And then there are more machine learning type of questions of how do you generalize appropriately, right? From one situation to the next. Just wanted to briefly say that this idea of building models of people, of individual human beings, how they make moral decisions, and then having those models vote is one that's been around for a couple of years now and has appeared in multiple places. I don't expect you to read this very wordy slide, but we did talk about this in our first paper. Ariel Procaccia and his group, first at CMU and they're now at Harvard, have also approached this in this way, and they have applied this kind of reasoning to self-driving cars, right? So situations in which a self-driving car has to make a trade-off between its occupants and other people on the road, and also in food donation. So to which entity do we allocate donated food? And I'll talk about a third one in just a little bit. But so first, what we need is some data of human moral judgments, right? That's what we're going to be able to learn from. I see there's some question in the chat. Is a machine learning decision probabilistic? Good question, right? So this is a question about aggregation. You could say, well, if 4% of people say it's not bad to steal the spot, then the model will steal the spot 4% of the time. You could do that, but it's not necessary. You could also go with majority vote and say, well, whatever is preferred the most often, that's what we should do. And this is really where we get into social choice theory, because there are all kinds of things you could do, right? This idea that we randomly pick one person's opinion in social choice is usually known as the random dictator model, right? We randomly pick one person, and that person then becomes the dictator in the sense that whatever that person wants to do, that's what we do. Usually we don't go with the random dictator model, but it's one model, and occasionally it has some advantages. But yeah, there we really go into social choice theory. But usually I would be inclined to go with the majority opinion, right? As long as there is, you can step back, and sometimes you might worry about the majority infringing on the minority's rights and so on. So, but just to a first approximation. Good. Okay, so we were looking for some data of human moral judgments. And my co-author, Walter Sinnott-Armstrong, who you saw in the straitjacket before, he had done an earlier study. He's actually pretty experimentally inclined. And in that study, they asked research subjects to evaluate scenarios such as the following. Right? So they were given some scenario, and then they were asked to say how morally wrong is the action described in that scenario. In this particular scenario, it's about a woman who throws a stapler at her colleague who is snoring during her talk. If I'm giving this talk live in person, at this point, I'd be looking around for a stapler. You're all quite safe over Zoom. But that's the kind of question, right? And so at first glance, maybe you say, oh, this is the kind of data that we need. That's human moral judgments. But the goal here is to be able to predict for new scenarios what humans would do. And because this is so open-ended, right? This is just general natural language. That's very hard to do. If we wanted to predict how people would judge a new scenario, it's first of all a problem in natural language processing, and most of them also would have some aspect of common sense reasoning, right? Like, how bad is it actually to throw a stapler at your colleague, right? If you think about it, well, that's actually pretty bad, right? Because the stapler is pretty hard and heavy and pointy. You can really hurt somebody throwing a stapler at, right? But that's the kind of like common sense physical reasoning that AI is actually not very good at yet. So we didn't want to do that. And instead we looked for something where the domain was a little bit narrower, or a lot narrower, and where we would clearly know what kind of some of the features were that we could use for machine learning. And we settled on kidney exchanges. I'll explain in a second what a kidney exchange is. This was, of course, so joint work with Rachel Friedman, who was a Duke undergraduate and is now a PhD student at Berkeley, for those of you at Berkeley. And also with John Dickerson, who is an expert on kidney exchanges, assistant professor at the University of Maryland. So this is about kidney exchanges. What are kidney exchanges, and what role does AI play in them? You could read this article over here that talks a little bit about our work and other people's work. But in brief, so first of all, your kidneys filter waste from your blood. Sometimes somebody's kidneys fail, at which point they may need a kidney transplant, right? So somebody else's kidney to be transplanted to them. Where could kidney transplants come from? Well, one way is from deceased organ donors, right? So somebody otherwise healthy is an organ donor and very unfortunately steps in front of a car and dies, but we can save the kidney and give that to somebody else. So that's great, but unfortunately not enough viable kidneys are made available through this route. Another thing that you could do is you could hope for a live donation. Human beings each have 2 kidneys, and if you're generally healthy, then you can survive with one. So you might find somebody who cares about you enough to give you one of their kidneys. Right? Now, one thing that can happen at that point is that you're medically not compatible. Right? So you have here this very dear friend who is willing to donate one of their kidneys on behalf of you, but it turns out due to blood types or some other reason, you actually cannot take the kidney. And you might think at that point, all you can do is say, well, thank you so much for offering. I better go look for somebody else. But there is actually still one thing that you can do. And that is to exchange. And this picture illustrates that. So here in this picture, we have a mother who wants to donate to her son, but they're not compatible, which is why that edge is crossed out. We have a husband that wants to donate to his wife. Also, they're not compatible, so that edge is crossed out. But it so turns out that the husband is compatible with the son and the mother with the wife. So the patients can swap donors. right? And that's considered okay. Now, in most of the world, it's illegal to buy and sell kidneys for money. It's also illegal to give valuable consideration for kidneys. I cannot say, well, if you give my wife a kidney, I'll give you a job. That's illegal. But swapping kidneys for kidneys is considered okay. Okay, so still not clear what AI has to do with this. Now imagine organizing a kidney exchange. What does that look like? So now you're organizing a kidney exchange, and you get a bunch of pairs of people in this way coming to your exchange. So we'll abstract a little bit. So now a vertex here is a pair of people where the donor wants to give on behalf of the patient. So donor 1 wants to give on behalf of patient 1 here on the left. And in parentheses, let's say is their blood type. So actually these two are not compatible because they have different blood types. And so we have these vertices, and then an edge indicates that one donor can give to another patient in another vertex. Okay, so there's an edge from the first vertex to the second one because the donor there can give to the patient in the second one. And so now here you could do two things. You could have vertices 1 and 2 swap with each other, right? So donor 1 could give to patient 2 and donor 2 to patient 1. That works. That leaves patient 3 out of the picture. Patient 3 doesn't get a kidney. Alternatively, you could match the second and third node together, right? So donor 2 gives to patient 3, donor 3 to patient 2. In this case, patient 1 is left out. And those are two solutions. It's not clear which one is better, but those are two things you could do. And then the bigger your exchange grows, the more decisions you have to make and the more complex this problem gets. Here's a slightly more complicated picture. And here what we see is there's two things here that you could do that would make sense. So first of all, on the left, you could have donor 1 give to patient 2 and donor 2 to patient 1. Right? That's the kind of thing we've been doing. A little bit more complicated is you could have donor 2 give to patient 4, donor 4 to patient 3, and donor 3 to patient 2. Then all of those people are happy as well. That's what we call a 3 cycle, right? Whereas the first kind of thing was a 2 cycle. And that would actually help 3 people. So that seems at first glance better. Okay, good. So and now as you imagine this graph getting bigger and bigger, this becomes a very hard optimization problem. It is in fact an NP-hard optimization problem, even for very simple versions of it. And there's lots of things that you can do with, in terms of modeling. You could model the arrival of future pairs of people and take that into account. So it's a very rich problem in that sense. I want to go back though to this very simple one. And here comes your next poll question. So now I want you to imagine we have to make this choice, right? Patient 2 here is going to be matched in any case, but is it patient 1 or patient 3 that gets matched? You might say, well, just toss a coin or something. But now I want you to imagine we know a little bit more about these people. So let's suppose that patient 1 is a 20-year-old Black student athlete who has a wonderful life ahead of her, except for this issue that her kidneys are failing. And let's say patient 3 is a 50-year-old white man with a long criminal record and a severe drinking problem, but also 3 children that depend on him. Okay, let's say that's the situation. Now, I'm not going to ask you to directly choose. What I'm going to ask you instead is, would you be willing to prioritize one over the other? I'm not going to ask you which one you would prioritize, but would you be willing to prioritize one over the other based on what I just told you? And generally, would you be inclined to make prioritization? So here, there's a bunch of choices. You can say, well, in this, what I just said, there you would prioritize, but and basically almost always you would prioritize. You might also say you would prioritize here, but that's, it's maybe kind of an extreme scenario. And in many cases, you would choose to toss a coin instead, or you would want to toss a coin here, but otherwise, but often you would actually prioritize, or you would almost always toss a coin. Or there's another option I gave you, which is you object to the whole way of presenting the problem. Okay, but then I do want you to think about, well, what else could you do, right? Because in some sense, this is the problem that you would end up facing. Maybe you object to presenting the problem in this way because there's some other feature that you think should be taken into account. Okay, fine. But that's not really what I want you to use that option for, right? What I want you to use that option for is really saying that something about this way of thinking is inherently wrong. Great. Okay, I'll leave it open. Okay, so now suddenly a lot of people are voting. Okay, great. I'm going to end the poll. And so in this audience, we actually have a lot of people who would say, oh, they'd almost always toss a coin, which I think is interesting because I gave the same talk, or pretty close to the same talk a little while ago, also in a computer science departmental seminar. And in that audience, for some reason, almost everybody wanted to prioritize. So it could be something about like just the way I just presented it, that I said something a little bit different, or maybe it's just a different audience. So that's interesting. But meanwhile, also quite a few people were willing to prioritize. So I think, and then there were a couple of people that objected to the way of presenting the problem. Does anybody want to kind of propose an alternative way of thinking about it? I'd be interested. I don't know if it's maybe not everybody can. By the way, also happy to take questions over email later. Oh, yeah, I think here's something in the chat. We should ask what person 2 wants. Okay, that's an interesting question as well, right? So it's kind of person 2's kidney. So that person gets to decide what happens with it. That might work in this particular example. I don't know if that generalizes to other settings. And now, first of all, there's also a question like, what about donor 2? Why shouldn't donor 2? Like it's donor 2's. I think here actually says person 2, so it's not clear if it's. I guess donor 2 would probably be more natural, right? Now we don't have to do it that way, right? We can also just say, well, everybody who, if you want to participate, then you have to kind of stick with the prioritization that's generally induced. In this particular example, you might ask donor 2. That's not a bad idea, but I'm not sure that you can make sense of that generally, right? Because generally things get more complicated, and it's not necessarily the case that you can have every individual deciding what happens with that person's kidney. Okay. Let me go ahead and close this. Okay, but so we pursued this line of, let's say that we wanted to, and also, of course, you might find a situation that donor 2 says, well, you know, I don't want to make that decision. You need to make it for me, right? Or I'll stick with whatever the default policy is because I don't want to have that on my mind. So in any case, let's pursue that line of reasoning that we set a policy for the exchange. Another issue here, by the way, here's another issue with asking donor 2. Here you can do that because it's pretty clear what the options are. Once you go to a sufficiently large instance where you have lots and lots of vertices, right? Now, the reason that AI is getting involved in this at all is just that it's too hard for a person to search through all the different possibilities, right? That's why we need computers to actually, even though it's an NP-hard problem, they can scale to looking at many different possible solutions, and that way find an optimal one. But it needs some guidance along the way as to what is actually valued, right? If it doesn't know what we actually try to optimize, then it's not clear to the algorithm which branches of the tree, of the search tree, it should pursue in finding good solutions. So that's another kind of difficulty with asking the individual people, because then do you keep asking them as the algorithm is searching through the space? That's a little bit tricky. So let's say we wanted to come up with an objective function. Now in this paper, we only considered the possibility, we only considered the situation where we would break ties. So we, based on this kind of moral objective. So we said, well, first of all, we're just maximizing the number of transplants. We're always going to do that. So in this example, it's clear we're going to do the 3-cycle, nothing is to be determined. So only in these kind of cases where you want to break ties, do we actually look, do we actually think about whether there are some features that we should take into account? Okay, there's another question of like, maybe we should ask clinicians which of 1 or 3 would get higher increased quality life years from the transplant. That's good. But in the end, there's still maybe going to be a question. So that's maybe, I consider that more a question about like what the features should be, right? And you're very right that maybe that's a more useful feature, at least if people understand what that means, to take into account. But when you're talking about trading off, like, you know, the person has kids that depend on him or her, versus the quality of the individual person's life, at some point it comes down to a moral judgment, I think, right? And it's not clear that there's any kind of natural unit in which we can express everything. Great. Okay, and there's a question of, let's find a Pareto frontier, right? So if there were a good way to sketch out the whole Pareto frontier, then maybe that would right? That actually people could kind of look at and analyze. That would be a nice way to approach this maybe as well. It's just not clear to me that you can do that very well, but if you could, that would be nice. Okay, good. So what we did was we asked a bunch of mechanical Turkers, Amazon mechanical Turkers, for their opinions. Now, we never thought that Amazon mechanical Turkers are the ideal audience to ask about this, but just as a proof of concept. And we first asked them what kind of features they would consider to be okay, or which ones should be taken into account and which ones should not be taken into account. And the answers to those were, they were generally okay with taking, or they felt that what should be taken into account includes age, medical condition, like both behavioral, like, this person is a heavy drinker or smoker, so we should take that into account, as well as non-behavioral, like this person has cancer in remission. Those people generally seem to agree should be taken into account. Then there were many things that people felt should not be taken into account, such as race or criminal record. And then there were some that were kind of on the boundary. Some people felt it should, and some people felt it shouldn't, like having dependents, like children that depend on the patient. So we took the 3 least controversial ones, and now we made a bunch of fictitious patients that varied only in these 3 attributes, age and 2 types of health. And that gave us actually, so 8 different fictitious patient profiles, 2 to the 3, right? Because for each attribute, you could independently choose whether the patient was, for example, 30 years old or 70 years old. And then we asked the mechanical Turkers to compare individual or pairs of patients and say, well, which one should be prioritized to receive the kidney? And here you see the results of that. And so here you see kind of how often they were preferred. And so somewhat unsurprisingly, the young, rarely drinking, otherwise healthy patient was preferred most often. And then you get this whole ranking effectively of the different types of profiles. Now, really, for the algorithm, you actually need to have also weights on the different profiles. There are different ways you can do that. One is with the Bradley-Terry statistical model. So in this model, every patient has a weight. And then the model says that the probability with which a patient is preferred to another one is proportional to the patient's score. Okay. So that gives you one way of getting weights. Now, it's maybe not the ideal weight, but in fact, it turns out that the weights don't really matter as much as the ranking, right? So the only extent to which the weights really matter is who is prioritized ahead of who. And we'll get some intuition about that in a little bit. And I wanted to just briefly show, so there are good simulators for kidney exchanges. And so we ran it in simulations just to see what would happen. And so we compared the standard algorithm, which is going to grade out boxes, and looking at how often each of the types of profiles would receive a kidney. And the standard algorithm just tries to maximize the number of kidneys that are transplanted, doesn't look at these profiles. And so unsurprisingly, the profile has kind of no impact on how often they're matched. But then our prioritized algorithm breaks ties by these kind of features. And so unsurprisingly, it helps to have the more prioritized features. There's an interesting thing that it kind of flattens out at the end. So I'll try to explain to you why it flattens out at the end, right? So it doesn't seem to just keep going down. The reason is that whether you get matched in one of these types of exchanges depends primarily on the blood type of both the patient and the donor in a pair. And some pairs are in a good situation that their donor is a universal donor blood type and their patient is a universal recipient blood type. And so they're going to be really easy to match. And in fact, we would love to have more of these types of pairs in the exchange because they help us match other people as well. So that is what we call an over-demanded pair, right? And then there are some other categories where, for example, they might have the patient and donor that actually have the same blood type, but there's some other reason they're not compatible, or one is A and one is B. But the trickiest category is the under-demanded. So that's kind of the inverse of the over-demanded. This might be, for example, that the patient has a universal donor blood type and the donor has a universal recipient blood type, which actually makes them really hard to match. And that's really where the trouble is. So basically in the large, once the kidney exchanges get large, the green, so the last 3 categories here, they're basically going to be fine. It's the under-demanded ones where the scarcity really is. And so if we look at the same kind of picture as before, but we zoom in only on the under-demanded pairs, we see why you get this flattening out. Because here, of course, there's a lower bound of 0. So what ends up happening is if you're under-demanded due to blood types and you use this prioritization, then well, what happens is, first of all, of course, the highly prioritized profiles, they really have a much better chance, but at the cost of giving the later ranked profiles basically a chance of 0. And that feels kind of uncomfortable, right? So now for some people, we've just totally taken away their chance of being matched. Right? And that at some level, that's kind of a sensible outcome, but is that really what we want? So we don't take a position on that, but it's kind of interesting to see kind of what happens in the large as a result of pursuing a policy like this. Okay, just briefly want to say, well, there's lots of interesting types of research questions that follow up from this. You can do theory, right? So we have, I'm just going to flash through these very quickly, but you can think in the Pac Learning framework, how many people should you actually ask these kind of queries? And how many queries should you ask each of them? And so we have a particular Pac Learning model where you can actually get these kind of formal results of, don't read the whole slide, but if you look at the bottom, you see, well, you need to ask a certain number of agents, a certain number of questions. Another kind of thing you can look at is behavioral concerns, right? So human beings maybe don't always act totally consistently or rationally in the way that we might like, and does that create any issues? Here we looked at the issue that if you tell people something about how the AI system is assessing them, like what the AI system thinks they're prioritizing, they start incorporating that and answering questions that way. And it turns out they do that even if the feedback was totally random, actually. Right? So if you tell people that the AI thinks that they care more about the life expectancy of the patients than how many dependents they have, even if that's just a totally random feedback, people start taking that into account to some extent and responding that way. So it's kind of on the border of whether it's significant or not. But that's a concern as well, because by asking more questions, usually you implicitly already give feedback about what the algorithm is thinking. So how do you correct for this? And then finally, the coin tossing, we actually have a paper on this at AAAI this year where we did allow subjects the option to toss coins. And it was interesting. So this is kind of interesting statistical modeling exercise because people vary a lot in whether they toss coins and or not, and also how they use the coin toss. Right? So there are different ways, different situations in which you might use the coin toss, and people use that differently as well. Okay, I'm going to end here with the part of learning objective functions. Any quick questions about that before I go to the second part? I think there's a Q&A here. Right, so is moral decision-making any different from more broadly predicting human decision-making? I think it probably is. There are some aspects that are different. For example, this coin tossing, right? I think that's something that where people behave pretty differently in some kind of morally laden context than in other contexts, right? Because like if it's more like which color car do you want, right? Then usually coin tossing is just about indifference, right? Like I don't really care like whether my car is orange or green or whatever. Just give me one, right? Whereas in the morally in situations with the moral component, I think there are often more fairness concerns, right? So people are maybe more inclined to toss coins, not because the two things are indistinct or the two options are indistinguishable to them, but because they worry about fairness and process and these types of issues. So I think in those ways, it can be different. And generally, we need to take a little bit more care as well, right? The one thing that we spent a lot of time thinking about is there are probably a lot of features that most people say shouldn't be taken into account, but if you present them, then they'll take them into account anyway, or at least some people will, right? And so how do you deal with that issue? That's maybe not as big of an issue, I would think, in other situations like which car is best for me. Okay, let me go on to the second part. We'll have more polls here still. And the second part is less about the objective function and less about ethical reasoning, and more about this issue of what are the boundaries of agents, and agents in some sense being, AI agents being very different from human agents in the kind of scenarios that they face in decision-making. And maybe like there are some extreme scenarios in which humans would also face those kind of questions. And because of that, some of these scenarios have actually been studied in the philosophy literature, but not so much beyond that. And so we'll see that. So I'm going to present a couple of these kind of issues, and then I'll present one extreme scenario where a human being might face that type of issue, but in reality, we're going to be more interested in AI facing this issue. So how should you act if you know that other people can read your code, right? If you're playing a game, but other people can read your code. It's usually not an issue for human beings. Maybe if somebody's looking at what's going on in your brain somehow, then maybe. But for AI, this might be a real issue. What if you know for certain that the person you're facing runs the same code as you? Now, for human beings, I don't know. Here's an example of two identical twins, Mark and Scott Kelly, who both became NASA astronauts. And so, they seem to make pretty similar choices in life. But even they made some different choices, right? One of them has a mustache. So, it's hard to see exactly the same thing in human beings. And then finally, what if you knew for sure that you had been in the same situation before, but you can't possibly remember what you did? Again, like, of course, I forget stuff all the time, but not in a very systematic way, right? You can go to like, movie 50 First Dates, so in which Drew Barrymore plays a character that every night forgets everything she learned the day before. But normally doesn't really happen so predictably in human beings. So let's look at some examples from the philosophy literature that bring this to the fore. First of all, Newcomb's demon. Some of you may already know this, but let me talk it through. And again, we'll do a poll on each of those. So hopefully that will be fun. Newcomb's demon. The story is as follows. There's a demon. Really, if you don't like demons, it can just be any good predictor, somebody who's a good predictor of human action and choices. The demon has two boxes and puts a positive amount of money in each of them. And now you don't get to see what's in the box, but you get to choose either. It's not maybe the choice you expect. It's the choice to either get the contents of box B or get the contents of both boxes. We also assume you like money. So at this point, it seems kind of like an obvious question, right? Like you should, well, no, the box A has a positive amount of money, so and whatever is in there is already in there, so I might as well take both boxes. But the twist is that the demon first predicted what you were going to do. And the demon is really, really good at this. So if the demon predicted that you would just take B, the demon is kind of going to reward you and put $1 million in box B and only 1,000 in box A. And if the demon predicted you would take both, then there's actually only $1,000 in each. And again, the demon is just incredibly accurate to really drive that home. Imagine that like the demon is not just playing this with you, but with a long queue of people. You're standing there in this queue. The demon predicted each one of them, and you look ahead and you see every time somebody picked one box, they walk away with $1 million. Every time somebody picks both boxes, they walk away with only $2,000, right? The demon is on fire, figuratively. And so now it's your choice. So what do you do? Okay. Right. So there's two conflicting intuitions here. Like, generally the people who pick only one box do a whole lot better, but whatever's in the boxes is already in the boxes, right? And you can't change that anymore. So how many boxes would you take? There's your poll, which I hope you can see. Yep. Would you take one? Would you take two boxes? Okay, I'll leave it open for just a little bit. Okay, interesting. It's pretty even. I'm going to close it. We have very slightly more two boxers, 52% versus 48%. Okay, interesting. Let's go to the next example, and we'll come back to this one. So now the prisoner's dilemma, which I assume everybody is familiar with, except unlike in the typical prisoner's dilemma, I want you to imagine playing against somebody who is very, very, very similar to yourself. Okay. So imagine that you have an identical twin. And not only is this your identical twin, but your entire life, you've always made the same decision, right? As kids, somebody asked you what flavor ice cream you want. Both of you said strawberry at the same time. And the next time you both said chocolate at the same, every single time it's the same time, it's the same thing, right? And now you're asked to play prisoner's dilemma against your twin. And you're still selfish. You care about your own payoff, not about your twin's payoff somehow. But you want to, right? But your twin is very much like you. So now one intuition is, well, defecting is always better, right? That's no matter what your twin does, defecting is better. That's what we typically learn in game theory. But another intuition is, look, if you cooperate, the chances are your twin also cooperates because you always do the same thing. And if you defect, chances are your twin also defects. And surely you're happier with both of you cooperating than with both of you defecting. So here comes the poll. What will you do? If I find it, will you cooperate or will you defect? Okay, I'll give you a couple more seconds. Okay, well here the people were very clear. 85% of people said to actually cooperate. Good. And you might think about the variant where like maybe once in your life you disagreed on something. And so would that change things for you? Let's not do a separate poll on that, but maybe that changes things for you. In any case, what we're really interested in is 2 copies of the same code, right? And then you can be pretty sure you're going to do the same thing. Here's another example that I made up myself, but I'm going to skip over it for time. But what's really going on in all these examples is that your own choice is evidence, right? Your own choice is evidence for what the daemon put in the boxes. It's evidence for whether your twin defects. And the same kind of thing happens in the third example. And now there are 2 kinds of decision theory, which usually don't come apart, but in these kind of examples, they do come apart. One kind of decision theory is what's known as evidential decision theory. And it says in these kind of situations, here's how you make decisions. You're going to look at all your options. When you look at one option, you say, okay, if I take that option, what does it tell me about the world? Update your beliefs. Now calculate your expected utility, given that you take that option. And do that for every option and pick the option that maximizes that. Whereas causal decision theory says, no, you shouldn't reason that way. You should only think about what you causally affect with your decision, as opposed to what your decision might be correlated with, but what you cannot affect. Okay, so in the examples we saw, evidential decision theory says you should take one box. Causal decision theory says, look, whatever's in the boxes you can't affect anymore. You might as well take both boxes because there's going to be more money in there. Prisoner's dilemma, similarly, evidential decision theory says you should cooperate because then the chances are a lot better that you both cooperate. Whereas causal decision theory says whatever your twin does, you can't affect that, so you might as well defect because that's always going to be better for you. I'm going to skip over a couple of things because I want to get to some other things. But we have a paper where we argue against causal decision theory in a Newcomb's demon-like kind of scenario with Casper Oesterheld, who is a PhD student here with me. So let me not go into that. Actually, later on, I'll argue against evidential decision theory. So I'm kind of in trouble because I've argued against basically every possible decision theory, which raises the question of what would I actually do? But we'll come back to that. Now I want to talk about something different. I want to talk about belief formation instead of decision making. And in particular, in settings with imperfect recall. Imperfect recall just means you forget some things. Again, I forget stuff all the time, but it really means settings where you are predictably forgetting things, right? And this actually can be useful in AI. It is used in poker playing AI for just scalability purposes. Let me not get into that. But also it could be used in AI because, for example, you want your self-driving car to forget where you just were before you hand it off to somebody else, right? So that kind of deliberate forgetting for privacy reasons. Or you might have a very broadly distributed system such that, we think about that whole system as one agent, but one node here takes an action and then another node takes an action without knowing what the other node did. And so in some sense, it's like the agent as a whole has forgotten what it just did, right? That's why these things are relevant. And it turns out belief formation gets pretty weird. So if you feel like you understand Bayesian reasoning and all that, hope to challenge that a little bit with what's known as the sleeping beauty problem. Okay, yet another problem we're going to do a poll for. Here's how the sleeping beauty problem works. We're going to say there's a participant in a study. This is just a story. Nobody is actually running these studies, right? But the participant in the story in the study is called Sleeping Beauty, and we'll be clear why in a second. So maybe some experiment on a university campus, imagine, And on Sunday, she's going to be given drugs to fall asleep. She'll be told about all this beforehand, by the way. She's going to fall asleep. Then the experimenter is going to toss a coin. It will land heads or tails. It's a fair coin. And that's going to determine what the experimenter does next. If the coin lands heads, here's what the experimenter is going to do. He's going to wake her up on Monday with a different cocktail of drugs. She's going to be awake for a little while, and then he's going to reuse the first cocktail of drugs to make her fall asleep again. Okay, and she's going to sleep all of Tuesday. On the other hand, if the coin lands tails, he's going to wake her up also on Monday, just like before, with heads. Then he's going to make her sleep again. But in this case, he's also going to wake her up on Tuesday. Okay, so the only difference in both cases, he will wake her up on Monday, but in the tails case, he will also wake her up on Tuesday. Okay, now the key thing is the imperfect recall part. Because of all these drugs, she's unable to form new memories, right? So you might say, well, if you wake up on Tuesday, you'll remember that you'd already been woken up on Monday. So you realize it's Tuesday, but no, you don't remember. Or you might feel like a lot of time has passed somehow. No. So if you're Sleeping Beauty, you cannot tell any of these three situations apart, whether you wake up with heads on Monday, with tails on Monday, or with tails on Tuesday. You can't tell them apart. So all you know is you've been woken up. And on top of that, you always know all the rules, right? So you don't forget the rules if you're Sleeping Beauty. So imagine that you are Sleeping Beauty and you've just been woken up. So you know it's either Monday or Tuesday. You know that the coin landed either heads or tails, but you don't know which one. But it's a question about probability, right? So if you believe in subjective probabilities, right, that you should have some belief about what the probability is, well, then we should say you should be able to answer somehow what is your subjective probability, your degree of belief. Typically, the way the question is phrased is, what is your belief that the coin landed heads? Right? Some probability, right? Some number from 0 to 1, presumably. But what is the number? We're going to do a poll about this, but first I want to see if anybody has a quick argument that they want to make for some number, or just intuitively, like what number seems to make sense. By the way, this one is a really fun one to do at like some kind of academic cocktail party with somewhat technically inclined people, because there will always be different opinions. And the key thing about this one, by the way, is that there still isn't really agreement on what the right answer is here, right? So unlike, the Monty Hall problem, which is maybe a little bit counterintuitive, but eventually everybody agrees on what the solution is, here that is not the case yet. Any takers for arguing for a particular number?
1/3.
Okay, why 1/3?
Well, because 1/3 of the time you're in the left branch.
1/3 of the time you're on the left branch,
So
right? So if you say,
yeah,
right. So you mean the top branch, I guess.
Yeah.
Okay. Right. So you say, okay, if you say that all these three in some sense have equal weight, then the top branch has only 1 and the bottom branch has 2. So it seems like 1/3 makes sense. Okay, good. Something in the chat. Okay. And so here we have an answer in the chat that, well, you can't remember anything. There is no evidence, so it should still be 1/2. Okay. We have actually now discovered the two main positions in the philosophy literature. There are two camps of people called the thirders and the halfers. Okay. So now we have already, and this, by the way, if you do this at a cocktail party, this will happen invariably. You will get both answers. And so, okay, let's go over the two arguments, or let me sort of build on two arguments. So first of all, there's a Sento's argument for 1/2 here in the chat, which says that, look, just to expand on it a little bit, right? On Sunday, before the whole thing happens, clearly you should believe that the coin will land heads with 1/2. That's obvious, right? That's just saying that the coin is fair. And then when you wake up, what have you learned, right? If you want to update your belief, you better have learned something. But you haven't learned anything because you always knew you were going to be woken up. Hence, it should still be 1/2. That's a typical halfer argument. Rupak gave an argument for 1/3. Let me give a little bit expanded version of that. Imagine now that you do this experiment once every week for a year. Kind of horrible. But imagine that we do that. And every week we toss the coin anew. Yes. And now you look back at the end of the year and you say, look, of all the times I woke up in the year, about a third of them were in heads weeks, right? A week where we tossed heads. So 1/3 is the right answer. Okay, so that didn't totally set. Right now we have 2 arguments. Oh, now I do the poll. So those of you who haven't spoken up and the ones that did speak up, let's see what you think. So are you a halfer? Are you a thirder? Do you actually have a different number in mind? Or do you feel like somehow things are not specified right? Or what's going on? Give this just a little bit more time. Okay, I'm going to close it. Good. In this particular audience, the thirders are a little bit more in number than the halfers. So it's almost twice as many thirders as halfers. Somebody said a different specific number, and 2 people said multiple numbers or poorly specified or something. Anybody want to speak up about what they thought? It's okay if you don't, but if you want to. Okay. Anyway, so 1/3 seems a little more popular. I'm actually also more on the 1/3 side, but there are very smart people also on the 1/2 side. So everybody is in good company. Why do we care about this in AI? So here's like an AI story that basically fits the Sleeping Beauty puzzle as well, right? So to really make it line up, imagine that we have low-level autonomy cars, so not really self-driving cars that you just let it drive, but what we see a little bit more today is that we might have cars that take over if the driver is making a major error. I fall asleep at the wheel, my car like adjusts and stays in the lane or something, right? So you could say, well, the AI kind of wakes up in that kind of situation. And let's say the car doesn't keep a record of such an event because I'm worried about my insurance or something like that. Okay, so here's on the bottom right is our driver. There are 2 types of drivers: good drivers who in the course of their driving career will make 1 major error, and bad ones that will make 2 major errors. And presumably here on the bottom right, we have a bad one. And so it's kind of, and if we say it's like 50-50 in the population, then we see a distribution that's pretty similar to what we see in the Sleeping Beauty problem, right? And in some sense, like now imagine you are the AI system and you wake up. Now you might care about what is the probability that the driver is a good driver, right? Because that might affect when you hand back control. And this is exactly the Sleeping Beauty puzzle. Okay. Should I go a little bit longer? We've had some questions we have like half an hour or more, or I want to make sure there's time for questions as well.
Yes, I think we can go a little bit longer. We have some time.
So please interrupt me with questions, but let me show a little bit how people have tried to make progress. Like, is it a third? Is it a half? Right? Is something not really specified, but everything seems to be specified. And now, so one way to make progress is to say, look, in the end, the purpose of all of this is making decisions, right? At least some people would argue that the reason we form beliefs is that we can make good decisions. And so we're going to see if we can get some clearly bad decisions from one or the other. And so the first argument goes against the halfer. So here's an idea that we can take advantage of halfers by doing the following. We're going to say, okay, whenever you awaken, we're going to offer you a bet, right? And then we're going to come up with a combination of bets that's clearly bad for you when you take them all. And it's important that we offer the bet every single time that she awakens, because otherwise you learn something from the bet, right? If I only offer bets on Mondays, then when you get a bet, you learn something. We don't want that to happen because we want the beliefs to stay the same. So let's say that we say, okay, well, every time you wake up, we offer you this bet. If you take the bet, then, and the coin landed heads, you're going to get 11. If it landed tails, you're going to have to pay 10. Now, the idea is that a halfer will accept this bet because a halfer says, well, both of these things happen with probability 1/2, and the upside is a little bit larger than the downside, assuming beauty is risk averse and risk neutral. But the thirder actually won't think this is a good idea. So the thirder won't take this bet. But now the thing is that what happens as a result, if the coin lands tails, actually beauty will be offered this bet twice and take it twice. And so she's going to end up with a payoff of -20 in the case of tails, because both of those bets will make her pay. And now this is starting to look a little bit bad for beauty, right? And in fact, it's not hard to combine this with another bet that is made on Sunday, just at which point everybody agrees on the beliefs, so that everything together results in a sure loss. So the argument is, if you're a halfer, you're going to take these bets, even when in combination, they'll result in a sure loss. That's clearly not a good thing to do. Hence, being a halfer is irrational. That's the argument. Okay. Now, the thing is, so now there was a counter argument in this literature that said, well, no, because what's going on here is you're implicitly assuming causal decision theory. You should use evidential decision theory. Because if you're an evidential decision theorist and a halfer, you actually won't take that first bet. Why? You would say, well, with probability 1/2, it's heads, because you're a halfer. If I accept, I'll get 11. But with probability 1/2 also, it is tails. And if I accept then that is very strong evidence for the fact that on the other day, I also accept the bet, right? What could be better evidence for me taking the bet on the other day than me taking it today, given that there's no distinction epistemically for me, right? And right, so if I accept, then I expect to accept the other day as well, and I expect to be unhappy. And whereas if I don't accept, then I expect also not to accept the other day. And so and the argument goes, if you're an evidential decision theorist and you're a halfer, you will not take the bet, and hence you won't fall for the Dutch book. Whereas the causal decision theorist will fall for it if the causal decision theorist is a halfer. Okay, try to get everything straight. Because you would say, well, whatever I do now is not going to affect what I do on the other day. Good. So it turns out if you're an evidential decision theorist thirder, you can also be Dutch booked. But in some sense, so these things end up going together. That if you're a causal decision theorist and you're a thirder, and you're an evidential decision theorist and a halfer, then you cannot be Dutch booked. Okay. Now we've seen that on some of the polls, people gave kind of the more evidential decision theory answer, right? Like with the prisoner's dilemma. And yet thirding was a little bit more popular. So that's maybe not a good combination. But some of these combinations are kind of safe in some sense. Though I have argued in somewhat richer settings, what I think is the natural interpretation of evidential decision theory still falls for Dutch books. So that's why I'm a little bit more on the thirder causal decision theory end. Okay, so maybe one more thing is, so I think it's kind of interesting because, so meanwhile, we're still stuck with this Sleeping Beauty problem. Like, is there really a right answer? And some people might say, well, it doesn't really matter as long as we make good decisions. But it feels to me like, it's kind of a well-specified problem, and there should be kind of a correct subjective belief, right? That's at least how I feel. And now this leaves me in the uncomfortable situation that, so if I'm a thirder, I should somehow be able to say what's wrong with the 1/2 argument, right? I have to say that somehow you learned something from waking up. So what did you learn? What are you conditioning on? So I think that what you're conditioning on is not the following. One thing you could say you're conditioning on is like, well, somewhere in time, there is an awakening, right? That's what you've learned, that somewhere in time, there is an awakening. And if that's all you've learned, you really have learned nothing, because you already knew that there was going to be at least one awakening somewhere in time. So I think what you learn is not somewhere in time there is an awakening, but I have just been awoken right now. Okay. And somehow I think that's different information than the other information. But it's kind of funny because this is what philosophers will call a centered fact. It's not a fact about the world objectively. It's a kind of subjective fact, right? And so just for fun, I'll show you here. I have a philosophy paper that's, some of the other papers are in philosophy journals, but this is kind of really a philosophy paper, and that like has no math or anything, but it's still kind of a computer scientist's philosophy paper in some sense. Because what this is about is the idea that like, what kind of fact is that, this kind of subjective fact? And so this paper illustrates that with by saying, like, imagine that you decide to go on a coding binge, and you code up this very rich simulation with simulated physics and simulated creatures that maybe doesn't work quite like our physics, but maybe there's something like light and all that. And you code it up, and let's say you're a brilliant programmer, you make no mistakes. I certainly make lots of mistakes, but you make no mistakes, except you made one mistake, which is you just forgot to print anything to the screen. So the thing is just running there silently. And so now presumably you're not happy. What you actually want is something to show up on your screen, right? Like maybe you want to see the perspective of one of the creatures. So this is maybe the perspective of the round-headed creature over here. But when you want to, you're going to have to do a little bit more work. You need to write a little bit more code that determines, for example, in which colors on the screen you display this simulated light. Okay. And so now the argument is from 30,000 feet in the paper is that our conscious experience is actually more like the second picture than the first picture, right? And in order to get to 2, you need to do a little bit more work, right? So in some sense, this additional bit of code that we just wrote about in which real-world colors to display is an additional fact about the subjective experience of the world. And that's the sense in which it's another fact. Okay, and so now so that's philosophy. Now you might just care about taking the right actions, right? Like making sure that our systems optimize appropriately. There are other variants of these kind of problems, such as the absent-minded driver problem. I won't take you through that in detail, but the idea here is that whether the decisions you make here will affect whether you're woken up again, right? You can exit the highway, but if you don't exit the highway, you might wake up again and you might not realize you made the decision before. So now you're actually in some sense in control over whether you wake up again. And it turns out that here there is a way to think kind of along third-order and causal decision theory lines that will always make you make the right decision. This is joint work with a couple of the people here, including besides Casper, I guess everybody is at Berkeley. So that's maybe also interesting. You can in some way get this to work with evidential decision theory, but you have to twist your brain in a really weird way where if you want that to work, you get things like you're about to toss a coin, a fair coin, that's going to determine your decision. And because you know it determines your decision, your belief that it comes up heads is actually not 1/2, even though you know the coin is fair. That's the kind of thing that you'll have to swallow, it seems, that if you still want to be an evidential decision theorist. And then finally, let me talk about one more thing, which is program equilibrium. So this is a different way of trying to avoid the prisoner's dilemma. So the idea is, suppose you can make your code legible to the other player's program. Then you can do things like this. Your strategy might be, or your program might be, if the other person's code is equal to my code, then I cooperate, and otherwise I defect. Okay, and this actually makes cooperate. So actually, this program, both players playing this program, is an equilibrium, right? If you think about it for a second, if you're in this situation, you don't want to deviate and have a different program, because at that point you'll make the other player stop cooperating. Makes sense. And this actually, I think, is just for the sake of the workshop, right? I know verification is of interest here as well. And this is actually something I'm interested in, where you can have, this is kind of very extreme, right? But you can imagine something like, self-driving cars, proving some properties about how they behave and making those properties legible to others on the road, right? Or maybe allowing others on the road to verify their code. And that would actually be a very useful thing for many purposes, right? It certainly would be a useful thing for figuring out how, as one of those self-driving cars, you ought to drive, and also for things like assigning responsibility, right? If somebody violates the kind of promise that they made about the code, then maybe we have some punitive action along those lines. So I think that that's a space where there may be interesting interactions with the verification community as well. I'll skip over a few more things. And let me just conclude that. So what's the point broadly of this talk? Traditionally, I think in AI, we've strived for something like the Homo economicus model, right? Which is often criticized as a model of people because people are not perfectly rational and optimizing. But when you criticize it as a model of AI, there's also reasons to do that, because the Homo economicus model also implicitly assumes that the entity is not distributed, has perfect memory, and somehow has tastes that are exogenously determined. And what I hope to have convinced you of is that doesn't always make sense for AI. where we need to think about choosing the objective function. We need to think about strategic ramification. We need to think about how beliefs are shared within the system. That leads to new questions about belief formation, decision making, and we've seen social choice, decision, and game theory all pop up. And I think those give a very solid foundation, but also there are a lot of open questions left. So thank you very much. I'll be happy to take some more questions if there are any.
Thanks, Vince. This was a really excellent discussion on the topic. So if you would like to ask a question, I think the easiest is if you just write Q on the chat, and then I can just call on you in order. And if you are one of the attendees, you can just raise hand or somehow try to write something Q on the Q&A, and I can unmute you. Kusha, perhaps you can start.
Okay.
Kusha? Yeah.
Hi. Thanks. I don't know if you can hear or see me, but
yes.
So good. One thing you didn't mention in terms of kind of coming up with these sort of moral decision-making entities is kind of striving for simplicity. And I wanted to mention something that struck me recently. So in the UK, there's a panel that decides on priority ordering for vaccinations in the UK vaccination program, right? And in their latest decisions about how to vaccinate people, below 50, they basically said just going by age group because of risks being higher with higher ages. And when they were explicitly asked about, well, why didn't you consider all kinds of other risk factors, like, for example, if somebody's a teacher or if somebody's a worker as a bus driver and so forth, then they said all of these are very valid, but adding lots of complexity to the decision-making process is itself something that damages the prospects of getting the vaccinations done in a timely manner, because an extremely complicated apparatus for deciding who goes next will actually itself cause problems and delays in doing the vaccinations. I'm mentioning this in the context of the kind of decision making around the kidney exchanges that you were talking about. And it might be that, for example, some decision, that kind of optimizes some moral criteria ends up creating huge cycles in the kidney transfer graph, which would be impractical to realize, right? So kind of simplicity seems to be a criterion that ought to be incorporated in these, but I'm not sure how one would do it in a formal way. I guess that's what I wanted to ask, actually.
Great. Yeah. Great
May I
question.
actually ask a very related question?
Yeah, go ahead.
So, very related to Kusha's point is that, would you say that an optimal algorithm for an NP-complete problem that takes 1,000 years is less moral than an approximation algorithm that only takes a month, but gives you a result that is 4 times worse than the optimal?
Makes sense. Okay, let me tackle the second one first. So yeah, so of course, if there's urgency to the decision, then of course you want to make a decision faster, right? That, for example, a self-driving car that's about to get in an accident, it can try to make the optimal decision, but by the time it does, it's run over a bunch of people, right? That's obviously not what we want. And this kind of gets into more general questions about bounded rationality, right? That that have been studied for a long time, at least outside of the ethical domain, right? But just the fact that, generally it's not rational to optimize your decisions to such a point that by the time you make it, it's already totally irrelevant, right? And so I think everybody agrees on that at a high level. Now the question is how you implement that precisely, right? So what is kind of the right way to be boundedly rational, right? Like if you say, well, Vince, I'm gonna give you money for like the value that you can obtain on these mixed integer programs. And so I don't give you optimal solutions. So you say, Vince, you're irrational because this other solution would have given you a higher amount of money. I say, look, I have the other, I just couldn't find it. Like, I'm just, maybe I'm not that smart, but that doesn't seem like the kind of rationality that we're worried about. So I think that that's a very good point. in most of what I've talked about, it's not clear that there are those time trade-offs. Well, so in self-driving cars, you want things to go fast in some sense, right? But the things that people have studied, you can run pretty fast. In the kidney exchanges, there could be the kind of scenario that Kusha sketched, I suppose, that somehow the solutions really change as a result of what you're doing, and it's going to take longer as a result. In practice, people manage to solve these things in time. There, of course, you have a little bit more time because the exchanges are run like once every so often. It varies which exchange you're talking about, but maybe once every month or at least once every week. I don't know. So you have a little bit more time to optimize. So definitely a good point. Now, the simplicity point. By the way, so here in the US, we also have vaccine prioritization. And as with many things in this pandemic, the US is kind of a distributed mess, or well, maybe you like it, but at least it's like kind of all over the place. And that creates its own issue. So here, actually, there is a much more complicated prioritization where they really try to think also about who's more likely to spread the virus, right? I think probably in the UK also healthcare workers were still vaccinated first, right? But so anyway, here they
yes, healthcare workers have already been vaccinated,
exactly.
But that was the justification for that is that they're likely to spread it to ill people in the hospital, and it was less for their own benefit, but for the patients at the hospital, kind of.
Absolutely. Yeah. But of course, so you might still make the argument that, well, some people outside hospitals are also far more likely to spread it than others, right? Like if the schools are opening, well, teachers, when there are outbreaks at schools, usually it seems from what I've read that the person spreading it is typically a teacher. So so you might, right? And meanwhile, also we want, maybe there are other considerations, right? Like here, schools have, at least it varies a lot in the US, but like here where we live, schools have been closed for a very long time. There's a lot of pressure to open back up. But the teachers unions are kind of resisting that. And so anything to get everybody to go along is great, right? So there are these other political considerations kind of beyond whether it's most helpful in preventing hospitalizations. But I do generally agree with you that there's some. So what are the benefits to simplicity? One is that it's easier to explain. One is, like, I guess there's some kind of overfitting that you might risk yourself doing, right? You might also worry, like kind of cynically, that the richer and more baroque you allow your policies to get, the more potential there is for people manipulating it in their own favor. Things also get more confusing and more messy, right? Like it's not really clear here in North Carolina, like how to interpret all the categories. Like I'm not sure if I'm in the current category or not, because like, professors are, but if you're not facing people, then maybe not. And so some people I know have already gotten vaccinated and some haven't. Like, so it's kind of and like people drive all over the place. So it's a little bit messier that way.
I guess this also fits into the paradigm of trying to do explainable AI, right? So this is also about explainability to the general public about why a certain policy about, let's say, kidney exchange or about vaccination might be instituted. And if the more complicated the policy is, obviously, the harder it is to explain.
Exactly. And there's justification, right? Why didn't I get a kidney? Well, if somebody has a question along those lines, they want to be able to answer that as well. I thought initially what you're going to say, so some of my colleagues at Oxford now have also been involved in the prioritization of IC beds, right? So that's hopefully we move away from needing that to more the vaccine problem, but there's still those kind of risks. So who should, if the intensive care is full, who should be prioritized to receive a bed, and which features should be taken into account. And it's a somewhat similar story, right? There's no real AI, I would say, involved in that particular decision, but otherwise it's a pretty similar story that you might take into account all kinds of other things, and whether people are smokers or and how old they are, how frail they are, all these kind of questions come up, and they've been looking at how to best address that. So I do agree that there's a benefit to simplicity, which was part of the reason that we didn't go too deep into the list of features, right? We didn't want to, because every feature you can find some people that care about that feature. Now there's a concern that it's wrong to use that feature, but I do agree there is a benefit to simplicity and not having too complicated of policies. And yeah, I wonder if there's kind of a formal way to think about that, right? Like in machine learning theory, there's kind of formal ways to think about Occam's razor. That doesn't seem to be quite what's going on here. It's not so much about generalizability as other benefits of simplicity. So that would be cool if there was kind of a formal result, but I don't really know what that would be.
There's a question on the Q&A, and maybe I can just reformulate it, but is there a connection between the Sleeping Beauty problem and the distinction between frequentist and Bayesian views? I guess a different way of setting this question is that suppose instead of being awoken twice, so on the heads you awake, you wake up Sleeping Beauty once, and on the tail side you wake her up 1 trillion times. And each time you wake her up, you ask whether to write down heads or tails. And this would be her subjective justification of what happened. So the frequentist view would go towards the thirders, right?
So first of all, that exact, so I remember giving, it was a different talk, but I did talk about a Sleeping Beauty problem at some point in a conference tutorial before the pandemic. So we were there in person, and we took a little bit more time to discuss various people's arguments. And one of them was a halfer, right? Or I don't remember which one was first. One of them was a thirder and tried to make the argument, clearly thirding is the right thing to do, because let's look at this exact extreme scenario of 1 trillion awakenings with tails. So clearly, then it should be, 1 in 1 trillion, basically. That was his argument. And a little bit later, somebody who was a halfer, who hadn't really paid close attention to the previous argument, made the argument and cited the exact same example. It's like, look, just imagine an example where, until you're awoken 1 trillion times. And so clearly, like, the answer should still be 1/2. And so, it's not clear that that example settles people's differing intuition. Now, about frequentist versus Bayesian, that's interesting. So the arguments I kind of gave suggested like one halving was maybe more associated with being a Bayesian, and thirding was more associated with being a frequentist, right? But I think that was just kind of an accident of the particular arguments that I gave in the way I presented them, rather than some kind of fundamental tie between the two, right? Because I think generally I am kind of a Bayesian in how I think about things, but I'm also a thirder. And I think that's actually consistent based on the little bit of a philosophical argument that I gave for that. But yeah, some of that is really kind of going into even metaphysics and philosophy of mind in some sense. But I don't think necessarily the halfer and thirder positions are tied to the frequentist and Bayesian positions. I think you can probably think about each of them, of each of the halfer and thirder positions in either frequentist or Bayesian perspectives if you twist your brain the right way, would be my sense.
Okay, thank you. We're almost out of time, but if there are other urgent questions, I can take them. Otherwise, of course, you can contact Vince and ask more questions.
Yes, please do.
Thank you again very much for agreeing to give the talk and for this wonderful talk and discussion. So next week we have Edith Elkind, who will talk about United for Change, deliberative coalition formation to change the status quo. So see you again next Friday, and thank you all for coming. And thanks, Vince, again for a wonderful talk.
Thanks everybody for being here, and thanks for inviting me.